Nelson. Down here we have Akash and Tony. We're from MySpace's core platform group. We've been responsible for our middle tier and other systems for a while now. And we're going to talk about some of the things we've done to scale MySpace and also how a library from the Robotic studio has helped us do that. So a little bit about who we are. MySpace is the largest social network that's based in LA. But we are the largest .NET website in the world. And as I'm sure you all know, you can't have a very large website without caching. So we have a very large caching tier to support that. Middle tier gets up to around 6 million requests a second at peak during the day. And we've got many terabytes of data stored in there. Also important for middle tier on a social network is data can't be stale. Users hate that. They want to see what they've done and what their friends have done right away with very little delay. So that's an issue that we've had to address constantly. And also for a lot of new and interesting features in social networking and websites in general, you need more than just a simple key value cache. So we'll talk about some of the things we've done in that area. Because of that, our system is called Data Relay because it does a lot more than just cache. And just to give you some perspective on the system, it's been in production since 2006. So we've been running it for a long time now. So you might also be wondering, what is CCR? I know it's not all that widespread of a library. It's called the Coordination and Concurrency Runtime. And it was originally part of a robotics toolkit, hence the name of this session. So this isn't really a session to teach you how to use CCR or all the things about it, but without a few bits of terminology, some of the stuff we talk about wouldn't make much sense. So some of the things that the library provides are thread pools, which are called dispatchers in the CCR API. There are job queues called dispatcher queues, unsurprisingly. And there's a set of class libraries called ports and an arbiter that allow you to connect the queues and the thread pools in various ways. And because graphs are cool, I thought I'd put some up there just to give a better perspective of some of the scale. Both of these are requests per second against some of our middle tier systems. The top one is from what we called shared, and it connects the user ID to the user's name and picture and basic information. As you can imagine, that's needed a lot. And that's topping out nearly 2 million requests a second just for that one system. And the bottom is one of the systems supporting our activity stream, which we're going to talk about in a lot more detail here. That, being a much heavier system, has a similar number of servers, but serving about 60,000 requests a second. So the stream. That is probably the most interesting thing going on most people's homepages for social networks. And it's also a great example for us to talk about because it's a cross-section of all of the different things that our middle tier has to do. As I mentioned, with all of the caching systems, you can't have stale data. And for the stream, that takes place in two different ways. There's both who you're interested in and what sort of activities and what they're doing. And you don't want either one of those to get out of date. You really only care about the people you care about, and you don't want to still see information about other things. Also, updates from our system don't just stay internal. There is searchability on Google. Updates go through the Twitter sync. And so it's not just a simple matter of updating a cache. Again, because big numbers are fun, our system serves about 60,000 queries a second, which, if you can do arithmetic, is about 5 billion a day. And we see about 35 million updates into that system. And last I checked, we've got about 5 terabytes of data needed to serve all of that. If you look at the functionality that the stream provides, you might reasonably ask, why not do it with a database? You could put together a couple of tables and a couple of queries, and it'd be pretty simple to do. One of the reasons we didn't do that is we decided that the whole thing should be based on publishers and not on subscribers. This goes back to the volatility of the data and what you're interested in. If we just painted a stream based on who you're interested in, what you're interested in at a given time, whenever anyone on that list did something, we'd have to update everything that every one of those person's followers' data, and that would be a pain. Also, and this is particular to us, but it also probably serves for anyone with a large amount of data, we have hundreds of databases with our users' information in it. So if we were going to do a query of all of your friends' information, that would be a massively distributed query, and that would just not perform well at all. Also, for any website that needs to be up all the time, like ours, you want to have as much decoupling as possible in various areas. So we still do have a database with this data in it, and that is our source of truth. But at the same time, it's written to our middle tier for reading, and all reads come out of the middle tier. All writes go to both. That ensures that if we have a problem reading, updates are not being affected. If we have a problem with the updating system, the reads are not affected. So generally, the system can keep on running, hopefully no matter what happens. So how did we do it? With robots that look exactly like that. Our data center is awesome. So, okay, how do robots have anything to do with this? Well, if you look at what a robot needs to do, it needs to coordinate a lot of inputs from sensors, a lot of outputs to arms, flamethrowers, whatever you might have. And you need all of that to be as decoupled as possible and very low latency. And if you look at what a server has to do, it's pretty much the same thing. You have inputs coming in from various places. You have queries coming in. All of these need to be happening at the same time, and hopefully not affecting each other in their latency or running. So to keep abusing this metaphor, look at the various tasks our robots have to do. Of course, they've got to be able to incorporate incoming messages that are coming from all over the site and many different sources. They need to be able to tell their neighbors about these messages because in our system, it's fairly heavily replicated so that any server being queried has the most up-to-date information. These messages have to be distributed very quickly. And of course, they have to be able to answer lots of questions about the data that they've incorporated into their own store, and also talk to other machines that have data if they need secondary information. And Akash will talk more about that because that features heavily into our implementation of the stream. And also, you have to be able to deal with other machines that are slow, that are not receiving updates, that are down. We have thousands of machines, so inevitably, there's always some that are down. So how does CCR help us do these things? If you look at all of these that are now highlighted, these are all handled by separate dispatchers within. So it's an easy way for us to have division of labor in the system. Again, I sort of hammer on the decoupling issue, but you don't want any backups at any point to affect the latency of any other part of this system. This one in particular, we've been able to do more interesting things with CCR than we would be able to do with just a simple thread pool and job system. This is one of the most heavily hit parts of the system because, as I mentioned, it's heavily replicated. One incoming server might have to replicate that message out to 30 other neighbors. So with thousands of updates a second, you can imagine it's tens of thousands of replication messages a second. So how does CCR help us do that? A big important thing is control of those job queues in ways other than just a FIFO sort of thing. And when you're looking at message distribution, you don't want to have every logical message be a separate network message. You want to be able to batch them as much as possible. But of course, that's not how they're coming in. They're coming in from all different sources, and they need to be collated. So the system that we came up with to do this, I call a sort of bucketed batch, because we need buckets to keep these messages. For the sake of the size of my fake bucket, say you want to batch groups of 6 messages. You get one that comes in. It kicks off a process that also sends something to what's called a timeout port in CCR that says, all right, do this thing after this amount of time has elapsed on the accumulated jobs. We also have something called a multiple receive running that will fire an action if we get to the limit. So, hey, we've gotten 5 messages in, but we've hit a 100 millisecond timeout because we really want these messages to be out as quickly as possible. So the timeout port will fire, the messages go, and the fake bucket turns back right side up. Also allows us to have a lot of different queues associated with each job pool. In our forwarding library, which handles this message distribution, we have a different queue effectively for every endpoint that's going to be simultaneously talked to, so that each of those queues don't have to walk over each other. And it also allows us to have a lot of control over the threads in each of those pools. Since we have different things doing different jobs, and these servers exist in a lot of different situations, we need a different number of threads to do different things. For example, the threads that are servicing actual queries, on some of the machines, we've got hundreds of gigs of data, so they tend to spend more time in I/O, and we need to increase the number of threads. In others, everything's in memory, it's very fast, we don't want a lot of contention, so we need to bring the number of threads down. And we can adjust this for all the different parts on the fly. So this is some of the issues that we've dealt with in a general sense for the overall system, but I haven't really talked about anything we've done to solve the stream yet. And to do that is Akash Patel.
Hello. Okay, so my name is Akash Patel, and I also work on various middle-tier systems at MySpace. And I'm going to continue talking about the stream. And for two reasons. One, the stream is essentially, arguably, the heart of a social networking system. And second, it's a great vehicle for us to talk about our middle-tier systems in a real example, world example. So the activity stream. Most people know what it is, but essentially, it's an aggregation of your friends' activities, right? And an activity is nothing but more or less a notification that occurs in the system. Now, these notifications can be generated in one of three ways, right? You can do it explicitly, you can do it implicitly, or it can be done on your behalf. So imagine you update your status and mood, like, I hope this talk doesn't take too long, I'm really hungry. That's a status update. You initialize, you basically explicitly raise an activity. Say you post a photo album of this conference, you know. That's, well, implicitly, you're notifying your friends, here's a check out my new photo album. And lastly, say you have a game installed and you reach a certain level and it notifies all your friends, like, you know, I'm amazing. So from a conceptual point of view, let's imagine this is you and you're a Smurf, and that's the extent of my artistic capabilities. And you have a couple of friends, right? You post a new status update, and what we do is we essentially create a really lightweight index associated to you. You post a new photo album. Well, that index gets updated. Now, again, I have to stress that this is a really lightweight index, and the actual activity associated to what you're doing is stored elsewhere. And let's not really worry about that right now. Let's just focus on the logistics of things here. So the index basically grows as you interact with the site and new activities are generated. And of course, this is happening for your friends too, right? Not just you. Now, you might say, what is this? Well, this is really a publisher-based cache. Why? Because the activities are associated to the user that generated it. But where's the activity stream? All you have is a list of activities that you generated. That's not interesting. You already know that. Well, the activity stream essentially is created by merging indexes from all your friends. And it's done essentially like that. That's very representative of how our system works, actually. And at the end, you have a merged activity feed, right? Now, something to note. This feed is extremely volatile. And it's volatile for many reasons. One is your friends are constantly generating new activities, right, if they're active. Secondly, you're going to add and remove friends, too. So that's going to change your activity feed. What else? Well, what if your friends change their privacy settings? Well, that's going to have an impact on what you see or what you don't see, from them at least. And then what happens if you change your preference of your activity stream? Like, you're like, I don't want to see any more video updates, I'm tired. Well, those are going to be removed from your stream. So if you want to cache that result, you can, but it comes at a cost. It comes at the cost of stale data. And we, as a middle tier group, we want to essentially provide up to real-time information to the presentation layer. That's our job. Why? Because the user experience needs to be optimal, and volatile data, is rarely cached like that. So a little bit about the stream architecture, right? So we use a system called Data Relay, which Eric talked about very briefly. And more or less, it's a message-based system, and there are just basically two kinds of messages in the system. There's the fire and forget, and then there's a round-trip message. And so what's an example of a fire and forget message, right? Well, you save something, you delete something, you update something. That's a fire and forget. From a client's point of view, This is a very asynchronous message. It doesn't care when you process it. It just says, here it is, go do it. On the other hand, you have a round-trip message, which is like a query or a get. In this case, obviously, the client is going to wait for a response. So from its point of view, it's a synchronous message. So that's the way you should think about it. And one of the other things that data relay brings is replication and clustering. And we'll talk about that in a second. Now, we've built a system on top of this messaging system called index cache. And it really represents, well, let's talk about what it's not. It's not a key value store. Because when you think of caching, almost everybody thinks about a key value store. A key value store offers really 4 operations, right? Create, retrieve, update, delete, CRUD. Index cache does more. It allows you to actually query. So it not only saves things, it stores them, but it allows you to query them. And we'll see that in a second. And one other thing to mention is that it's a 2-tiered system, meaning the index and the data are stored separately. And this is very crucial for scaling. So let's talk about data relay real quick, a crash course. You have the concept of a group, you have the concept of a cluster, and you have a concept of a node. Okay? What are nodes? Nodes are like your little robots. They process messages. They talk to their neighbors. They represent processing capability. They represent storage capability. They could do whatever really you need them to do. And you take these nodes and you group them into something called a cluster. Okay, now what does that do? Well, this allows you to basically partition your data, if you're working with data, across these clusters, right? So let's say you have 300 gigs of data, right? Well, if you do it this way, then you're going to get 100 gig in cluster 1, 100 gig in cluster 2, and 100 gig in cluster 3. Now, why do we have multiple nodes in a cluster? Why? First of all, they're all replicas. They all have the same exact set of data. And you might say, well, that's kind of weird, because if you just have 2 nodes, isn't that enough in the case of failover if one node goes bad? Well, that's not really the issue here. The issue here is the volume of traffic. If you're serving, as Eric mentioned, the volume of traffic we serve, we can't just rely on 2 nodes. So we need, depending on the kind of traffic, for which cache group, we might need more clusters or less clusters. But the point is, these clusters are actually, one other thing, these clusters are very resilient. Because, well, I'll talk about that in a second here. So the whole thing is called a group, essentially. The whole entity is called a group. And nodes need to talk to each other, right? We said they need to talk to their peers. And by peers, I mean nodes within the cluster. Why? Probably for replication. And then they sometimes need to talk to other nodes in other clusters. Why? Well, maybe for a query that's a little bit advanced. And then surely they need to talk to other groups. Why? Because they might have data elsewhere that they need access to. So going back to the resilience of the cluster, well, think about this. Imagine node 2 gets a little bit unstable. What's going to happen? Well, node 2 is going to go down. All the clients are going to shift to node 1 and node 3. That's good and great. But now while node 2 is down, whether it's 5 minutes or half an hour, it's missing out on a bunch of replication messages, right? Because node 1 and node 3 are sending messages that are not being delivered. So what node 1 and node 3 do is they keep actually a queue, saying, when node 2 comes up, I'm going to catch it up with all the data that it's missed. So that's what I mean by these clusters are very resilient. Okay, so now let's get back to the activity stream, right? So here's an activities index group at MySpace, let's say. Let's assume that's the makeup of it, okay? And just to remind you, what we're storing in this group are those lightweight indexes, okay? Okay, so let's focus on that. So let's assume that we have a couple of users in cluster 1, a couple of users in cluster 2, and cluster 3. Now your friends, obviously, are going to be spread throughout these clusters because you don't make friends based on where we put them. Now, let's say a new activity message comes into our system. What happens? The first thing we do is we figure out which cluster that message should go to, because we know the user associated to that activity message is in one of those 3 clusters. Well, we use some sort of a mapping to figure out that, so that's pretty simple. What do we do then? We basically update the index. I don't know, that's fine. So, okay, so we have a message that goes to node 1, and the index is updated. Well, obviously, node 2 and node 3 also have that index, and it also needs to be updated, right? So replication occurs. Now let's kind of zoom in on the interaction between node 1 and node 2 for a moment, right? From node 1's point of view, it has these things. The best, I guess, description is a proxy. For every endpoint node 1 talks to, it has a proxy to that endpoint. So this is not actually node 2. This is a proxy to node 2. Okay? It's the destination node. Now, the first thing that happens in this proxy is that you identify that message as a fire and forget message. Because what is this? It's just an update message. What does that mean? Well, from CCR point of view, this is where it all comes in. So I'm going to kind of go through this quickly and then talk about some of these constructs. So basically, a message gets put into a port. Okay? And a port is nothing but a queue. And what is it a queue for? Well, items in the port really store arguments for a delegate. So let's see. We have the concept of arbiters and dispatcher queues. Now, what are arbiters? It's just a mechanism. It's a mechanism to coordinate activity between ports and dispatcher queues. Well, then what's a dispatcher queue? Well, that's where you put things, that's where you put a task, so it gets scheduled. Okay, it's just a queue full of delegates, really. And if you're familiar with the .NET CLR thread pool, you've probably written the line thread pool dot queue user work item. What you're doing is very similar. You're saying, here's a task I want to schedule. When a thread becomes available, execute it. Well, we do the same thing with the thread pool. And in CCR, they're called dispatchers. So there's a lot of things we can talk about here. But basically, I want to say that there's a lot of constructs here that are specific to this node proxy, right? Like the ports and the arbiters and the dispatcher queue. But the thread pools are not specific to a proxy. That'd be silly. If node 1 was communicating with, let's say, 100 other nodes, it'd be silly to have 100 thread pools. So really, the thread pools are shared across all proxies, okay? And what they do is they actually do a round robin from all the dispatcher queues. So that's worth noting. So that's another feature of CCR we really like. One other thing we like is the thread pool itself. Eric mentioned that we can set the size of that thread pool. If we want to, we can also change the number of threads in that thread pool. Well, not really, though. What we do is we create a whole new thread pool, and we swap it in place. And you might say, why do you want to do that? Well, at runtime, we might realize that we're I/O bound. We push a new config, and suddenly now, instead of X threads, we have Y threads. And I've drawn basically two sides of this here. And for one reason, basically, there's two things going on here in this proxy. You have all the fire and forget messages, and you have all the round-trip messages. And remember, the end game in all this is we want to bucket our logical messages into one single message for the transport. So that last red arrow you see, really, is going to basically package those messages and send them over like a TCP socket. So that's how a new activity is processed. What about a request for the actual activity stream? Okay, so here's a client. And it's basically going to say, here, I need for you guys to create me the activity stream. And in it, really, it's a query. In it, what you have is a set of, let's say, friend IDs. It's a list of your friends. It's saying, from these friends, give me the activity stream. Of course, there's also some other settings, but that's kind of immaterial. Now, what happens is we know that your friends are probably scattered throughout all our clusters. What we do is we create a subquery targeted for cluster 1 that has only the friends that live in cluster 1. Again, we can do this because it's a simple mapping function. And we do the same thing for cluster 2 and cluster 3. So let's talk about what happens when when a client wants to talk to node 1, let's say, from cluster 1. Well, this is the same picture you saw earlier. And this time, we're going to focus on the right side of the diagram. Well, why? Because it's a round-trip message. It's a query, right? Again, it goes through a similar set of constructs, CCR constructs. The port here is a slightly different port than the one on the other side. And that's because we don't want to use a timeout port for these kinds of messages. Why? Because we want to process messages very quickly, especially if they're synchronous from the point of view of client, right? You don't really want to wait too long. So that's essentially that. So going back to our activity stream, what happens? Well, cluster 1 produces a result of all your friends there. So that's the activity stream from cluster 1. And that's very similar to what I showed earlier, where you merge up things. And of course, cluster 2 does the same exact thing, and cluster 3 does the same thing. Now, you ideally want a query result that merges all those things together. So you do that. And what you now have is a very lightweight activity stream. You don't actually have the activities yet. You only have references to them. At which point, you actually go to that key value store that I talked about earlier, and you say, you know what, for these activities that I'm interested in, go ahead and fetch the corresponding data. This is the last step that we do. And by the way, those queries that were split off, they're all done in parallel. So this is not all that amazing when you have 6 friends, but imagine you have 600 friends or 2,000 friends. Now you need to make your response time as short as possible. So you can have lots of clusters, you can do a lot of parallel processing, and essentially get your result very quickly. Then you send the activity response back to the client, right? At this point, the client is usually the presentation tier. It'll do whatever it wants to do at that. Let's look at that graph that Eric mentioned. Now, this is a slightly different set of graphs. The top one is the same graph. It's the 60,000 queries per second peak. Now you guys kind of have an idea of what that box is doing. But if you look at, this is the same box now. This is a different set of statistics on the bottom. If you look at that, the second graph, you'll see that we're actually examining 1.6 million indexes per second in order to serve those 60,000 queries per second. So there's a lot of work that's occurring here. So that kind of gives you an appreciation of the kind of load we have and why we design our systems the way we do. And just a quick word about index cache, the system that powers the activity stream. It's really our de facto distributed querying platform. When we need to filter, merge, and sort things, we use index cache. And it's essentially ubiquitous at MySpace whenever a key value store is not enough, right? It's in the activity stream, it's in our videos verticals, it's in our music verticals, it's in our open social or MySpace developer platform verticals. It's in a lot of places. So essentially, what is the point? Well, robots are processing your every move. And by that, I mean those CCR constructs that I discussed. So those are the ports, the arbiters, the dispatcher queues, and the dispatchers. And out of all these things, the dispatchers are shared, as I discussed. And specifically, those are the constructs within CCR that we use. So if you're interested, you can look those up. Last thing, thread pool flexibility. We like the idea of being able to set our own thread pool sizes. We like the idea of hooking up queues to our thread pools, and that is really important to us. So now, activities don't just live at MySpace, right? MySpace activities actually find themselves bubbling up to other systems, like Twitter and Google. I mean, maybe you're aware, or not. In Google, you can actually do a search of status updates or activities, essentially, and MySpace activities show up. And obviously, Twitter, there's a project called Twitter Sync that allows you to sync your activities from MySpace and Twitter. So talk about that now. Tony's going to come up and take it over.
Thank you, Akash. Hello, my name is Tony Chow. I work with Akash and Eric on middle-tier systems at MySpace. And as Akash said, MySpace activities are everywhere. One of those places happens to be Google. The evidence for that is that when you do a search on Google nowadays, MySpace activities may show up with in the results, along with the web pages hits. Basically, every single status update on MySpace, every single comment, every single waking thought of MySpace users are now being indexed by Google in real time within seconds of being posted. And in this part of the presentation, I will basically talk about how this happens. Now, the technology at MySpace that makes it possible for Google to tap into MySpace activities is called officially the real-time stream. And what real-time stream is, it's basically a service that pushes user activities out to subscribers using Google's pub/sub/hubbub standard, which is an extension of the Atom and RSS feed for data streaming. And basically, this system is completely open, completely free, and basically anyone, any application developer, can subscribe to the real-time stream. We launched this service at the end of last year, and the major subscribers so far include Google, Groovy, OneWrite, among many others. And currently, we're streaming about 100 million messages per day to all subscribers all over the internet. And to understand the challenges behind creating something like the real-time stream, let's first take a look at the design for implementing it that is simple, straightforward, and completely doesn't work. Imagine users sitting at their computers, right? They log into MySpace. The browser start to talk to MySpace servers. The MySpace, specifically the MySpace front-end web servers. The web servers are where activities originate. And in this model, the web servers generate activities and push them directly out to subscribers. Subscribers like Google, Groovy, WinRiot, and let's say slow.com. Now, the system will work as long as all the subscribers are perfectly fast and perfectly cooperative. But if only one of the subscribers misbehave, is slow or unresponsive, our web servers will start tanking. And browsers will start timing out, and the user experience will go down the drain. So what this is illustrating is the basic problem behind the push model of content distribution, which is that you're putting yourself at the mercy of machines that don't belong to you, that you have no control over. If these machines break, you can't really fix them quickly. And a working streaming architecture has to be able to handle situations like this elegantly without breaking itself. So the specific challenges are, we must be able to protect the user experience. Now, real-time streaming is a very cool feature, but the user experience on MySpace itself, on the mothership, must never be compromised. We have to be able to deliver a constant stream of activities to subscribers that can handle the traffic. In other words, we have to be performant, otherwise we wouldn't be real-time. We have to give all subscribers a fair chance at trying at handling our traffic, because we are open to all. On the other hand, if subscribers misbehave, we must prevent them from doing any damage, either to ourselves or to other subscribers. Now, let's take a look at the actual streaming architecture in MySpace from a high-level perspective. Still, users talk to, operate their browsers. The browsers talk to the web servers. And the web servers generate activities, and instead of sending them directly to subscribers, in our model, they send them to another tier of servers called the activities filter. The activities filter is a set of servers that's responsible for taking the activities, finding subscribers that are interested in these activities, and compose XML atom messages that specifically target those subscribers. These messages are then asynchronously sent to Transaction Manager, which ultimately, which is another tier of servers, by the way. And Transaction Manager who is ultimately responsible for delivering the messages out to subscribers. Now, since the communication between the three tiers of servers are asynchronous, when subscribers tank, the front end is not affected, thereby preserving the user experience. Of course, we have not addressed all the challenges yet, because we've merely moved the problem from the front end to Transaction Manager, which still have to ultimately fairly and intelligently deal with misbehaving subscribers. And let's see how it does it. So this is one Transaction Manager server. It can talk to any number of subscribers. When one subscriber starts being slow or unresponsive, the first thing we do is that we queue against it. And queuing is important because it allows the subscriber to some time to recover, so that when it does become fast again, it can process what's in the queue again without losing any data. However, a simple queuing model would be insufficient because it'll block healthy subscribers from receiving messages. To handle that, our second measure is to partition one queue into many queues, dynamically scaled as we talk to more and more subscribers. This way, one subscriber can queue all day long without affecting other subscribers. Another typical problem that's encountered with slow subscribers and talking to slow web servers in general from a multi-threaded application like Transaction Manager is that slow subscribers tend to hog all the threads. And this will deprive other subscribers of valuable traffic. And to solve that problem, we employ throttling, which basically restricts the maximum number of simultaneous connections that can be made to any given subscriber. This way, we prevent thread starvation from occurring. Another measure that we employ is that we make massive use of asynchronous I/O operations. And this makes much more efficient use of the threads and also prevents thread starvation. Now, queuing, partitioning, throttling, and async I/O are sufficient as long as all the subscribers are only occasionally slow and mostly performant. However, because we're open to all, because we allow all just anyone to subscribe to our stream, we very frequently run into subscribers that are just chronically slow. They subscribe, they don't have the hardware or the expertise to handle the stream traffic, and they just can't perform. For these subscribers, we want to give them a fair chance at trying. However, we cannot allow them to hog our system resources forever. And for these subscribers, we need more drastic measures. And one of those measures is that we sometimes discard messages. When a queue against a subscriber reaches a certain limit, we simply discard new messages from coming into the queue. This effectively caps the amount of resources that can be consumed by a subscriber. Additionally, we keep track of how many times a subscriber times out. If this number exceeds a certain threshold within a given time period, Transaction Manager will inform back to Activities Filter and basically say, please suspend the subscription. And this will stop new messages from coming into the queue, basically. And we'll continue to process transaction messages that are already in the queue, and they will eventually all time out. The queue will deplete, and we'll stop talking to the subscriber. And this basically is how Transaction Manager polices the stream. Now, Transaction Manager is an ideal platform for the streaming purpose. However, Transaction Manager was not invented for the real-time stream. As it happens, all of the problems that I talked about that we encountered with talking to subscribers, we also encountered over the years talking to our own servers in our own data farm. And Transaction Manager was actually initially designed as a general platform for reliable persistence in MySpace, within MySpace. It can not only send generic HTTP requests like it should for streaming. It can also make SQL calls, SOAP calls, RESTful API calls, and SMTP calls, among others. And major features of MySpace rely on Transaction Manager for persistence, including MySpace Mail, basic social networking feature, friend requests, also basic, status mood update, even more basic, and many, many more. Now, what does CCR have to do with Transaction Manager? First of all, Transaction Manager is built on data relay. And since, as Akash and Eric mentioned and described, CCR is integral to how data relay works. So by the virtue of that, it already takes full advantage of CCR. However, Transaction Manager internally by itself makes an entirely different use of CCR. It uses the CCR iterator pattern for helping us to make asynchronous I/O calls. Now, what is the CCR iterator pattern? To understand this pattern, we first of all have to understand what asynchronous I/O is. Now, when most of us write a data-driven application that talks to a database server, for example, or web servers, we're making these calls synchronously. It means that our thread is being held until the server responds. In other words, synchronous I/O is blocking. This is okay for most cases, right? For most applications. But when you're building an application like Transaction Manager that has to make hundreds, if not thousands, of simultaneous I/O calls, doing so synchronously requires that you use a lot of threads. And a lot of threads is really bad for performance, as it happens, because threads are not free. The more threads you have, the more context switching you have to do. And context switching eats up CPU cycles. This is why synchronous I/O is not very scalable. Now, Transaction Manager makes all of its I/O calls against subscribers asynchronously. Asynchronous I/O is not blocking, which means that the thread only has to initiate the call to a remote service. And afterwards, it's free to do other things. Therefore, with asynchronous I/O, you need a lot fewer threads, and all those threads are actually busy doing things as opposed to just hanging around. As a result, asynchronous I/O scales much more effectively. However, there's a drawback to asynchronous I/O programming. The drawback is that of complexity. Asynchronous I/O, in a program that's written using asynchronous I/O would look completely different from one that's written to call services synchronously. It's very hard to program, and even worse, the code that it generates, that you end up writing, is very, very hard to read. And hard to read code means unmaintainable code, and unmaintainable code means buggy code. And this is where the CCR iterator pattern comes in. In a nutshell, the CCR iterator pattern is something that allows you to, is a better way to write asynchronous code. Now, how many of you in the audience have used the C# iterators before? Plenty, of course, because we are all programmers here. And basically, C# iterators is a feature in the C# language introduced in version 2.0 that allows you to, that gives you an easier way to write enumerators. Instead of implementing the whole enumerator interface, you simply write a method with a bunch of yield return calls in them. CCR has the ability to tap into C# iterators and employ them for a new purpose. The purpose of making asynchronous programming easier. The code that you end up with still behaves asynchronously, but looks like synchronous code. To demonstrate the difference that the CCR iterator pattern makes, let me show you some code snippets. Now, let's say you want to write a simple method that makes two SQL Server calls, and you want to do them consecutively, but asynchronously. This is the code that you have to write. As you can see, you have to use nested callback delegates. This is kind of hard to read and difficult to figure out what's going on. And things get even more out of hand if you have you need to make like dozens, even hundreds of nested calls. In comparison, if you write this using the CCR iterator pattern, this is the code that you would see. As you can see, you end up with flat lines with no nesting, and that indicate clearly what the progression of events are. And this is obviously much, much cleaner code. It's much more maintainable, and it's also far less bug prone. And as far as we're concerned at MySpace, the CCR iterator pattern is basically an indispensable tool for asynchronous programming. It makes asynchronous programming a far more realistic proposition. And if you're interested in, if you're doing asynchronous programming, and you have not used this pattern before, we highly recommend that you check it out. Just search for CCR iterators on Google, and Jeffrey Rector also has written extensively on the pattern. And this concludes my part of the presentation, and I'll now hand the program back to Eric.
Thank you, Tony. All right, so we've talked some about how our overall messaging system works, how our index cache system works, and how Transaction Manager works. You might have noticed we didn't show, well, Tony showed some, but many code samples. Part of that is it's a pretty big topic, and it's hard to figure out exactly which parts and exactly what you guys might be interested in. And the other reason is because we're going to share a lot more than samples. I don't know if that font's big enough. So most of what we've talked about today is now open sourced. Available right now, if you go to datarelay.codeplex.com, you can download the source for all of Data Relay, our C# and managed C++ Berkeley DB wrapper, which is what we use for most of our key value storage, all of the index cache system, our network transport, serialization. It's exactly what we use in production. Right now, Transaction Manager is not up there, but we plan on getting that up there soon. It's quite a bit of work to get our source code ready for that. And thought you might be interested in places in the code base that use CCR. The bucketed batch system is inside of the forwarding component, and it's in that file and that method. I don't think I really need to read these because you're not going to remember. You're just going to look at the slide later. Just have to ask you to fill out the evaluations that are everywhere, because that makes these presentations better for everyone. And I would love to open up to questions. This is a really big topic. We didn't really know what parts you all might be interested in us focusing on, so we're certainly happy to answer any questions you might have, either now or if you dive into that source and have questions for us later, feel free to contact us at our email addresses. Oh, yeah. As I just reminded, we also did an interview on the Channel 9, which is Microsoft's website for video interviews with people. And we talk more about the architecture of data relay there. It's a slightly different focus. We cover some of the same ground. But you might want to check that out as well. And now, if anyone has any questions. No? Yeah, please come up to the microphone.
Hello.
Hi.
I was wondering, with respect to the asynchronous processing, have you looked at all at the task parallel library, the TPL, and compared and contrast that in your internal development team? And secondly, with respect to maybe moving some of the asynchronicity out to the edge, have you looked at the reactive framework?
Oh, as far as the task library, it's kind of designed to address kind of different problems. Asynchronous I/O is responsible for is something that you use to basically make more efficient use of threads. Whereas the task parallel library, as I understand it, although I haven't worked with it closely, is basically makes it easier for you to farm out work to multiple threads. So it's not quite comparable. As far as the reaction library, no, I haven't looked at it.
As for the parallel libraries, we've looked at it somewhat, and it's definitely really interesting. But as I mentioned, we've had this in production since 2006, and it's been using CCR the whole time, and CCR was available then. So, sure.
Hey, can you guys explain how you get the share knowledge about CCR and how to get other teams using it? Because I know it's expanded throughout all different parts of MySpace. How do you get developers up to speed on it and the way that you're using it?
Well, for one thing, there's a lot of good information out there already online. So if you just search for CCR, there's actually very good articles that will compare and contrast things with the .NET CLR thread pool. There's a lot of guidance out there alone from Microsoft. So there's a lot of Microsoft documentation that's really excellent. And it sounds a lot harder than it is. So once you get familiar with some of this, some of the wordings that CCR uses, it's really not that bad. So personally, I just went to documentation. I started reading it. That's how I learned about it. But within MySpace, I don't know, Eric, is there?
I think largely we've just shown people what we had done already, and once you see some examples, it becomes clear pretty quickly.
Great talk.
Thank you.
Can you speak a little bit about how you handle failure in your fire and forget messages, so the worker dies or the message gets lost?
Yeah. As we mentioned, internally, we keep queues of any message. And we also have, inside the code model, the forwarding component is basically keeping an instance of a class for every remote endpoint. And each of those endpoints keeps track of an error queue. So if it has any sort of communication failure, that message is just requeued and tried again on a timer. As far as the server processing that message, for our basic fire and forget messages, we don't have a confirmation. We do have a save with confirm and various other confirmed messages, but of course those require being synchronous. We don't have anything that will go back up and tell the original submitter of the message that something went wrong. But it's just responsible for getting the message across the wire, and once it's there, it is hopeful, I guess.
And I think it's worth repeating what Eric just said, which is we do have messages which are fire and forget messages that are confirmed so that there's some sort of a guarantee that the message was actually delivered.
Yeah, since in most cases, these updates are coming directly from web servers due to user action, and we didn't really want to leave the feedback loop in place because that inevitably leads to queuing on the front end if there's any slowdown. But we've got other systems that will feed the middle tier, reading out of a database called populators. Those tend to use the confirmed updates because it's okay if they queue up a little bit.
So you mentioned you were using an indexing layer to collect the streams. Is that Michael Garsky's Lucene work?
No, that is different. I know he has worked with Lucene, and I know that team has worked with CCR as well, but I'm not too familiar. This is our internally served stuff as opposed to the search.
Are you doing like long-term search on that? Is that a similar architecture for your long-term social search?
I am not sure how those searches are put together, actually. This is all just the real-time serving for the web page. And as far as data warehousing and other issues, they're actually completely separate teams, so I'm not quite sure.
Cool, thanks.
Mm-hmm.
Yeah, do you use MSMQ for your queuing services?
No. It's been, sadly, our experience along the line that most of the time that we use a pre-rolled product, it falls over in some way. MSMQ, I think we use it for some things. It's great for a reliable queue, but our internal queues are just implemented for this specific task for performance reasons.
So Windows Activation Services, you don't use that either?
No. And we used to use remoting, but ended up writing our own socket transport as well. At our scale, things tend to get weird. Anyone else? All right, well, I guess that's it. As I said, I'll be happy to answer questions in this email, and I certainly hope you check out the project on CodePlex. It's probably a little bit intimidating, but we will definitely be updating it over time with more documentation and more sample clients.
And please fill out a feedback form, please.